Imagine this. Thousands of years ago, a Babylonian writer looked at a clay tablet struggling with a practical problem like dividing a field or collecting taxes. At the heart of these issues lay a single powerful question. How do you find an unknown value? Nowadays, we give that unknown a simple name, x. But we're so used to this humble letter that we rarely stop to think, where did it come from? Back then, there was no x, no plus sign, and no equal sign. How did the great thinkers of the ancient world solve for the unknown using different methods, forms, and symbols? The quest to solve for x, which is closely tied to the history of algebra, became the key to unlocking everything from the secrets of the pyramids to the architecture of our modern technological world. In this video, we'll explore how the ancient Egyptians and Mesopotamians solved the unknown, early steps in the long journey toward algebra. Let's step back in time and begin the adventure. Welcome to ancient Egypt. The scribes used math for a range of practical problems, which required them to solve for unknowns. Most of what we know comes from only a few surviving texts, most famously the Rind and Moscow papyri, along with fragments such as the Berlin, Reisner, and Cahun papyri. Many of the problems were rooted in daily life, but the papyri also include more abstract puzzles. In the Rind papyrus, we find problems like this. A quantity and its seventh added together become 19. That's the original, but to make the method clearer, let's look at a simpler version with a quarter instead of a seventh. A quantity and its quarter added together become 15. In our modern language, we'd immediately write x plus 1/4 equals 15. Simple enough, right? But the Egyptian scribe had no x. They called this unknown quantity aha, or a heap. So how did they do it? They used a wonderfully clever and intuitive method, which we now call the method of false position. The idea is simple. Instead of struggling to find the right answer, let's start by making a wrong guess, but an easy one. What's a really easy number to calculate a quarter of? Well, how about 4? Okay, so let's guess that aha is 4. If we calculate it, 4 plus its quarter, which is 1, gives us 5. This is obviously wrong. The answer we want is 15, not 5. But here's the genius part. They didn't see 5 as a wrong answer. They saw it as a key. They asked, what do I need to multiply our result, 5, by to get the correct result, 15? The answer is 3. Our result needs to be scaled up by a factor of 3. Now, because mathematics is fair and this relationship is linear, that means our initial guess must also be scaled up by that same factor of 3. So, we take our initial guess, 4, multiply it by our correction factor, 3, and we get 12. Let's check it. 12 plus its quarter, 3, is 15. Perfect. Without any formal algebra, just an easy guess and proportional reasoning, they could solve complex problems. But what about harder problems? Those involving squares? The Egyptians did solve quadratic type problems, but only in practical case-specific forms, as in the Berlin Papyrus 6619. For a more systematic treatment of quadratic equations, we must travel to Mesopotamia, to the Babylonian civilization, which we will discuss in the next section. Mesopotamian scribes didn't use x either. They wrote in cuneiform and left thousands of clay tablets, some with surprisingly advanced ideas. Consider an old Babylonian example from the tablet MS 5112. In modern wording, it says, the field and twice its side add up to 120. What is the side? With modern mathematics, we would write x squared plus 2x equals 120. This is a quadratic equation. The simple guessing method from Egypt won't work here. The relationship is no longer linear. So what did the Babylonians do? They thought visually. They didn't see x squared as a symbol. They saw it as a square. And the 2x, they saw it as a rectangle with side x and side 2. So the problem became a geometric challenge. Construct a shape from this square and this rectangle, whose total area is 120, and find the side length x. And here comes their stroke of genius, a procedure you might recognize from math class, completing the square. They took the rectangle representing 2x and they split it in two. One half stays put, the other half, they moved to the bottom. Look at the shape now. It's almost a larger square, isn't it? There's just one little piece missing in the corner to make it perfect. What's the size of that missing piece? Since we split that rectangle of 2 in half, the missing piece is a small square, 1 by 1. Its area is 1. So let's add this piece in. By adding an area of 1, they had literally completed the square. But remember, an equation must be balanced. If we add 1 to the left side, we must also add 1 to the right. So the right side, which was 120, becomes 121. Now look what we have. On one hand, a perfect completed square. On the other, we know its total area is 121. If a square has an area of 121, what is its side length? It must be the square root of 121, which is 11. We can also see from the drawing that the side length of this big square is x plus 1. So x plus 1 must equal 11. From here, we can easily see that x equals 10. Beautiful. This visual technique wasn't just for one problem. It was a procedure that works every time for equations of the specific form x squared plus bx equals c. The steps are always the same. Take the rectangle representing bx and split it in half. Place the pieces around the x squared square, forming that familiar L shape. The missing corner piece, we always have an area of b over 2 squared. By adding this to both sides of the equation, you create a perfect square, whose side is x plus b over 2. In modern notation, we can express it as you see here. However, it's important to emphasize that this notation is only used to explain the method in our mathematical language today. The Mesopotamians themselves had nothing to do with equations or formulas in this form. Their approach was entirely geometric. For example, consider another quadratic equation, what we now view as two versions of the same problem, differing only by the sign of b. They regarded as distinct problems, each with its own geometric interpretation. This ancient geometric procedure, born from cutting and rearranging shapes, is the direct ancestor of the quadratic formula we use today. The next time you solve an equation, take a moment to appreciate the thousands of years of human ingenuity packed inside it.